Really hard.
Okay, just before I start, last time after I finished, people came to me and asked me some questions. So when I ask in class if anybody has a question, you should ask them, because then I don't have to answer it only once, not 10 times. So ask your questions, don't worry. So basically before these guys get ready, so let me just explain to you what I'm going to do. So we are going to solve one LP example again, just do it the way we did in class, but this time it's a bigger one and has more calculations, just to make sure that you feel comfortable with those calculations. Then it seems that the first question people had problem with what's MLE. So I'm going to say what's MLE, and then if you have any other question about this homework, you can obviously ask. I'm not going to solve it for you, but we'll do something like near solving. Just a second. And then the first lecture there was this optimization problem, which was this graph. I'm going to just solve it at the end if anybody has a problem. And also, if anybody has any problem with Excel solver, I can solve an example. So that's what I had in mind. This is obviously more than what I can cover, but just feel free to ask any question in the middle about any other thing. I'm fine. If I know, I will tell you. If I don't know, I will tell you next time. No problem. Let's just see if these guys are ready. Hello? Okay, since that we are all set. Okay, so let's just start with the LP problem and make sure that we are on the same line about LP. Okay, the first thing that I wanted to talk about is a little bit about the geometry of the feasible region and what does it mean, basically. So we had two ways. We talked that we can talk about the feasible region in sense of inequalities. So we showed them something like this: x greater than or equal to 0. Yeah, question? Okay. Or if you don't feel comfortable with this notation, you can always think of it like this. But you'd better start feeling comfortable with those, because at some point, we are going to end up using them a lot. So this is a case of a 2x2 matrix. Okay, let's see. So you can think of the feasible regions like this, or you can think of them as equalities. Now, we will show that basically they are the same. There is no difference in them. But these are easier to think of, these are harder to think of. But these are easier to solve, these are harder to solve in a sense of just calculation. By harder, I mean more calculation, nothing more than that. So we are going to think of them this way, solve them this way. That's a little bit funny. So let's think of it. What do we mean here in a very simple example, which I really don't need even that one. So x1 plus x2 less than equal to 10. Any number really. 10 is big. 2. So, and obviously x1 and x2 greater than equal to 0. So let's see what this means. This means that you draw the line x1 plus x2 equals to 2. It would be this line. Okay, this is our line. And then we want it to be smaller than 2, so we mean this side of the line. So basically our feasible region, because these two have to be positive, this side and this side, so our feasible region would be something like this. Okay? Now, instead of looking at the feasible region but something like this, we can think of something like x1 plus x2 plus s is equal to 2. S comes from the slack. That's why I just use S. You can use anything. x1 and x2 and s are greater than equal to 0. Okay? So this is obviously the points that are feasible here are exactly the same points that are feasible here. well, a little different. We'll talk about the difference right now. And the points that are here are just the points that are here. So this x1 and x2 that satisfy this, they are also satisfied here with some s. That's it. But let's draw this one and see what this one looks like. This one looks like this. Questions? So, this one looks like x1, x2, and s. So it would look like something like this. If you have questions, you can ask me. Okay, so this would be a plane. So this is the plane that I've drawn here. So there's nothing inside it. So 0, 0, 0 obviously is not on this one. So this is the plane that we would be solving our problem in. So the feasible region of this one is a two-dimensional plane. Well, by two-dimensional I mean that, well, not two-dimensional. In this plane, the feasible region of this one is this other plane. They are obviously different. You know, they are not the same objects. Okay, this is the first thing. But the idea is, if you solve the problem on this feasible region and this feasible region, they give you the same result. Why? Because think of some point. I shouldn't have drawn this. Think of some point in this plane, somewhere here. So this is somewhere in the air. It's not on this plane. Okay. So this point has a projection on the plane below it. Something like here. So you pick a point on the plane, you project it here. This one has an x1 and an x2. So basically, when we are talking about a point x1 and x2 here, which is a point like this, it's as if we are talking about a point in a three-dimensional space, which is here. You can see it a little bit further from the whiteboard, somewhere here, standing here. So the point up here or the point down here, they are the same point for our reasons, because they have the same coordinates. The first and their first and second coordinates are the same. So now let's see why we, well, okay, forget that for the time being. So this is the idea that why these two things are the same. This is no proof or anything. I'm just giving an intuition that what's happening when you move from this kind of representation to this kind of representation. There is a small difference. This is a two-dimensional problem. This is a three-dimensional problem. Okay. So, for example, in if you are solving a two-dimensional problem, everything is two-dimensional. You know that the optimal solution is either one of these corner points or it's one of the boundaries. But we talk that maybe the whole thing can be the feasible region. That's when, for example, when you have a three-dimensional vector which is perpendicular to the whole thing. So there is a small differences, but for our reasons, they are not that much different. Just this was an idea of how to move from this notation to this notation. Now, thinking of inequalities, there is a small difference also in thinking about them that you should be careful. When we talk in this kind of representation, which everything is less than equal, you draw some line, one side or the other side of the line. Maybe you talk about a three-dimensional inequality. That's also fine, because that one we can also imagine it, but not more than this. So this less than 2, this would be everything also positive. So this would be this plane and everything inside it. So unlike this one, which is everything only on the plane, this one would be everything inside the plane up to this point. So it would be a pyramid. Now, when you think of inequalities, then you would be talking about something that you can move inside it. But when you are talking about equalities, it restricts your space. For example, this is an equation of a plane. So when you are talking about a constraint like this one, it means that in a three-dimensional space, you're just walking on one plane. Basically, you can look at it in a two-dimensional space and lose nothing. So that's a little bit of thinking, just you want to think about it. So these are not going to be tested anywhere. I just want you to make you feel comfortable with these things. So when you're talking about inequalities, you cannot reduce the dimension anymore. You cannot think of this thing. This is a two-dimensional shape, and you cannot think of it in a one-dimensional space because you have some area. But here it's an equality, and you're talking in a three-dimensional space. But this one is restricting your space to one dimension lower. So basically, we can think of this thing, which is a three-dimensional object, in a two-dimensional space, which is this. Basically the same shape that we have here. So just think of it like this, that when you have equality constraints, you can think of it in it. Now, it's hard to work with these guys. Why? Let me give you an example. Assume that you have a problem like this. Less than 5, x1 minus x2 is less than 2. Okay, these are three inequalities. And well, this is not a really good shape. I'm just drawing something. Okay, so don't even bother thinking of what I'm drawing. It might be totally wrong. So it might be something like this. So you have three inequalities, 2 dimensions. Nice. You draw it. You can think of it. But assume that we want to look at this in this second representation. Then it would be x1 plus x2 plus s1 equals, then plus s2 equals, then plus s3 equals. It's already 5-dimensional. There is no way you can even think of it. So that's why all the examples that you would see are in form of inequalities, because you can have a lot of constraints and still imagine that idea. But otherwise, you couldn't do that. It's hard to think of it. But even though it's hard to think of it, but you know that you have a 5-dimensional space, that there are three equality constraints, so it's as if you're working on a plane, which is basically what we are doing here. But you can never imagine what that thing is. So it was just a feeling of why they are the same and how they are different. So now with this, they are the same objects, but one of them is easier to think of, the other one is easier to give an algorithm for. Now, let's go and do an example to see what happened in class last time. Maybe it was a little bit confusing. And this is going to be a little bit long example, so bear with me. But I think you might like it, because it has a lot of calculation and should make you feel comfortable after this, that these problems are not hard at all. So, maximize, this is my objective function. x1 plus 6x2. And these are my constraints. Minus 2x1 plus x2 is less than or equal to 2. I call it 1. x1 plus x2 is less than or equal to 5. I call it 2. x2 is less than or equal to 3. I call it 3. 2x1 plus x2 is less than or equal to 8. I call it 4. And 2x1 minus x2 is less than or equal to 6. I call it 5. x1, x2 is greater than or equal to 0. Well, by all this stuff that I said right now, the only thing that you should know is that we can think of this thing, obviously. So we start drawing the feasible region of this problem. So our feasible region would look like x1, x2. So let's start drawing. Well, this is easy. 1, 2, 3. This would be the third constraint. And I want it this way, to be less than equal. Then we draw this one.
You're very tall.
Sorry? Okay. I don't know. So if we put x1 equals to 0, x2 would be 2. And then 1, 2, 3, 4, 5. I put x1 equals to half. Well, not half. A 1. Then this should be 4. Okay, somewhere here. Okay. So this would be my first constraint. And I want it this way. Then x1 plus x2 is equal to 5. 1, 2, 3, 4, 5. 5. Okay, my lines are not very correct, but still. So this is the second constraint. And then the fourth constraint would be if we put x1 equals to 2, then x2 would be 4, somewhere here. And then we put x1 equals to 4, 1, 2, 3, 4. This one would be 0. So it would be something like this. Yes. And then the last one, I put x It looks like this. I have the shape here, so I really don't bother to draw it anymore. Looks like this. So this is the fifth one, and this is the fourth one. So our feasible region would look like this. Okay. So we'll be solving this, we'll be maximizing this function over that point. And for the time being, we always assume, well, you can see when you have a problem in this format, there's also another nice thing. 0, 0 is always a feasible solution. So finding the easy starting point is really easy here. You can always start from 0, 0 because it's feasible. But here, it's not necessarily feasible. So we know one easy point too. Assume that we know nothing about geometry, so we cannot find these points. Nothing is really for the time being. So we have 0, 0. Okay. Now we start moving from 0, 0 in. So what we learned last time was that for finding the optimal solution, we only need to check these points, which we call them vertices, corner points, basic feasible solution, extreme point, all these names. It has a lot of names. Now, so we just have to check this. And we learned that we have a method, which we called it simplex, which started moving from here then to the neighbor, 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 until it found the optimal solution. Okay, so the first thing that you have to do is to check whether you want to move in this direction or you want to move in this direction. That's the first thing that we did last time. So let's see how we did this one. Stop me wherever I'm being confusing or there's something that is missing. I might make mistakes still, so just correct me. Now, let's see how this guy works. What did I do here? Okay. So, the first thing that you have to look is, let's call this direction A, and let's call this direction B. Okay. So first I'm checking direction A. If I move in direction A, let's see how my objective function would change. Okay. So I want to look at the rate of change in my objective function. Okay. Now, when I move in this direction, A, x1 wouldn't change. It would remain 0, 0, 0. But x2 would start increasing. So if this is the objective function, the rate of change would be 6 times rate of change of x2. This is just normal differential, nothing really fancy. And is my x2 increasing or decreasing? My x2 is increasing, so this would be a positive value. So this would be greater than 0. So this would tell me that if I start moving in this direction, I'm improving my objective function. Okay, so I'm going in a good direction, not a bad direction, basically. We also check B. Direction B. In direction B, x1 is increasing and x2 is not increasing. So this would be dx1. Again, it would be 0, greater than 0, because I'm going in this direction and I'm increasing. So it means that both directions are good. Now, there are a billion methods out there to pick which one. We really don't care that much, so we just pick this one. Why? Because I have calculations for that one here. If you want to do, in fact, I would recommend to do it at the end if you wanted. It's not really. Try to move in this direction. So try to choose B for yourself and just do it, to feel comfortable with it. Sorry? Okay.
But how do you decide in this direction?
Both of them are correct. None of them would be wrong. There are different methods to tell you. Nobody knows. Nobody knows. Don't worry. There are different methods to choose them. Don't worry at all. We are not really worried about technicality. I just want to say that it doesn't matter. As long as you're consistent, you apply the same rule. It's fine. Okay. For the time being, let us do this. We will look at the coefficient of the differential. Whichever one is bigger, we choose that one. Okay. So I go in that direction. Let's see what happens in that direction. When I'm moving in this direction, The first thing that I told you was that, okay, maybe I skipped one step, but that's fine. That we are going to give our algorithm for the equality case, not the inequality case. So since I know my algorithm for the equality case, I have to change this problem to equality form. So let's write that thing down too. I need that one too. So it would be minus 2x1 plus x2 plus s1 equals to 2 plus s2 plus s3 plus s4 plus s5 equal minus 2x1 plus x2 x1 plus x2 x2 plus x3 2x1 plus x2 and 2x1 minus x2 equals to 2, 5, 3, 8, 6. And x for all I, xi, and si are greater than or equal to 0. Nothing changed. I just, changed the representation. Now, let's see what's going to happen. I'm going to start increasing x1. So obviously, if I don't change anything else, no other variable changes, then all of these constraints will be violated. Why? Because at 0, 0, everything is satisfied, everything is nice. Oh, something to remember. So now we have, instead of a 2-dimensional problem, we have a 7-dimensional problem. So our variables are this: 0, 0, 2, 5, 3, 8, 6. So x1, x2, s1 till s5. Okay, so now you have 7. You're in a 7 dimension. So 0, 0, 2, 5, 3, 8, 6 satisfies these constraints. Now what we are doing, we're going to start increasing x2, the second one. If nothing else changes, obviously this will be violated. There is no doubt on that. So when we start changing these, we have to change the others in a way that these are satisfied still. So writing that would be writing it something like this. So let me find what I have here, because the calculations are a little bit tedious. So we will have something like this. Now I'm going to switch to vector and matrices to make it nicer. So x1 would remain 0. So this wouldn't have any effect. So we write the vector for x2. It would be 1, 1, 1, 1, minus 1. Okay? Plus, let's write down the matrix which is multiplied by this guy. Oops, sorry. dx1. S1, S2, S3, S4, S5, D equals to 0. So let's see what I wrote. Just for a second, don't write down and listen to what I'm saying. So I said that x2 plus s1 was equal to 2. Okay, this one I knew. Now I'm changing x2 to something called x2 prime, a new value. x2 prime plus, obviously s1 changes too. s1 prime should still be equal to 2, because this should be satisfied. So deduct these two from each other. It would be x prime 2 minus x2. Let me write up there. So this would give me x prime 2 minus x2 plus s prime 1 minus s1 equals to 0. Okay? Now this is the change in x2. This is the change in s1 equals to 0. So what I wrote here as a matrix is nothing but just looking at these equations before changing the new variables, after applying before looking at these equations, having the initial values, and then the values after I change x1 a little. So since both of them should be satisfied, I deduct them. I say the rate of changing, the amount of change in this one plus the amount of change in the second one should be 0. So I wrote it for each equation, and then I wrote it in a nice format as a matrix. Oh, x2. Yes, thank you. Thank you. Somebody notices. It seems that, Even if one person looks at this board, I'm fine. So now, simplifying these guys would give you this. Would give you, so I'm going to write it fast, ds1 equals minus dx2, ds2 equals minus dx2, ds3 equals minus dx2, ds4 equals minus dx2, ds5 equals dx2. There is no minus here. So, just multiplying it, writing it nicely. So I'm just switching between matrix and equations to just, yes?
Can you simplify the matrix from the equation?
Oh, okay. Let me tell you how I got the matrix. Let me see what I need, really. Okay, I'm going to write it here because I need that part. So I'm going to have a set of equations like this. Okay. The first equation was dx2 plus ds1 equals to 0. Okay. Then from the second one, keeping this one constant, I get another equation. It would be dx2 plus ds2 equals to 0. Okay? dx2 plus ds3 equals to 0. And also for the 4, it's exactly the same thing. But for the fifth one, it's a minus one. So minus dx2 plus ds4 is equals to 0. Okay? Now I want to write these guys in a matrix format. So let's look at what's happening here. What's happening here is this. If you multiply dx by these guys, it would be dx2, 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 dx2 minus dx2. This is just this vector multiplied by dx2. Now, this is the identity matrix. Let's say 0, 0, 0, 0, 0. How many zeros? 5 zeros. Okay, and everything here is also 0. So now multiply this matrix by this vector. It would be 1 multiplied by ds1, the rest are 0. So this would give me ds1. The second one would give me ds2 until the last one, which will give ds5, equals to 0, 0, 0, 0, 0. Now this is just exactly the same thing as this. Okay? Good. So you should feel comfortable, just switching between matrices and equations, Okay. So now we have these constraints. We know that, we have these relations that if we change dx2, we have to change the others by these values. Now, let's start doing it. So we start increasing dx2 until we hit a line. What's the meaning of hitting a line? It means that, okay, now this is the point. When you are standing on one of these lines, no, I think we are standing here, somewhere in between. It means that all these inequalities are in fact strict inequalities. When you are somewhere inside. None of them are satisfied at equality. But for example, let us think of moving in this direction until we hit this guy. When you hit the line, you are on line number 2. So this line number 2 is, in fact, when you are standing here, it's satisfied at equality. Okay? So in general, all of them are inequality. Now, so standing at 0, 0, it means that 2 of these inequalities are satisfied strictly. What are those inequalities? These 2 inequalities. Now we start moving from this one until we hit this. So now we know which one it is. This is number 1. So we know that this one would turn out to be equality, and the one which was x2 greater than equal to 0, this one would not be equality anymore. It would change to be inequality. Well, this one is an easy question. You can always look at the picture and find it out. But in a billion variable problem, you cannot do it. So you have to have a method of finding which inequality becomes strict. So now we need a method to not just look at the picture and say, okay, this is number 1. We need to look at our equations and find a way to that. So what does this mean? This means that when we start moving in this direction, the slack variable for equation number 1, the slack variable was S1. Its value was 2. So I'm getting near to this line. The slack variable is smaller, smaller, smaller until it hits 0. So I can go as much as I hit that slack variable. But at the same time, when I'm going towards this one, I'm also going towards this other line equation. So the slack variable for the third one is also decreasing. So all these slack variables are changing. How? We know how they are changing. So we look at the change. We know how much they're changing. We know what was their initial value, because we know the initial value of all the s's. And we know how they are changing. So we start increasing x1 until the first one hits 0. If you can increase x1, we know that increasing x2, sorry. If you know that increasing x2 is good, because if you increase x2, your objective function would go up. If you can increase x2 and never hit 0, then your problem is unbounded. It means that you have an infinite solution. It's like this. Maximize x1 given x1 is greater than or equal to 0. This is obviously infinity. You can just go up as much as you want. So this would be a test for us in our algorithm, which I think Professor Engar would tell you formally next time, how to do the mechanics. It would be a test to see if we are unbounded or not. Now, let's start increasing it. This is the main idea. Let's start increasing our variables and see where we hit it. Now, okay, I have S1 let me find my equations, otherwise I would make a mistake. Okay, good. So we know that S1, S2, let's write it as, okay, now I have to give a name to this to make it easier for you. Okay, now this is one name that we introduced last time. Those that are 0, we call them non-basic variable. Those that are non-zero, we call them basic variable. What do we mean by basic and non-basic? If you look at this set of equations, we have 7 variables and 5 equations. So there's infinite number of solutions. The way we solve it, we put 2 of them 0, 5 variable, 5 equation, we solve it. Those two that we put them 0, we call them non-basic. Those that are found through the solution of that 5 by 5 equations and 5 variables, we call them basic variables. So these are non-basic variables, these are the basic variables. Now, the vector of my basic variables has the value 2, 5, 3, 8, 6. Okay? Now, this vector is going to change. How? This way. Plus ds1, ds2, ds3, ds4, and ds5. So this is s1, s2, s3, s4, s5. So these are the s's, and they are going to be added with the change in the s, because we are changing them. We want these guys to be greater than or equal to 0. We want our variables always to remain positive. So we will write it. I'm going to write it. I will need this one, so let's keep this stuff there. So let's write that one and see what shows up. So we will have 2 plus. What's the value for ds1? The value for ds1 is minus dx2. Minus dx2 has to be greater than or equal to 0. The second one tells you 5 plus ds2, which is again minus dx2, is greater than or equal to 0. And so on. 8. And the last one is 6 plus dx2 is greater than or equal to 0. So what happens? These are just the new values for these guys. I'm just saying by changing these things, these values should still remain positive. That's all the things. So these are going to give you bounds on dx2. This one is going to give you dx2 is less than or equal to 2, dx2 is less than or equal to 5, dx2 is less than or equal to 3, dx2 is less than or equal to 8, and dx2 is greater than or equal to minus 6. Now, from this one you should guess that this means even if you go up to infinity, you will never violate this constraint. Let's see which constraint is this one. This is the last constraint, this one. This is this line. That everything above it is feasible. If you are here and you go up to infinity, you would never violate this one. But everything else would be violated. But the smallest one is this. So you are allowed to change your x2 by 2. So we do it. And then we are fine. So we change x2 from 0 to 2. Let's see what happens. x1 would remain the same thing as 0. It was 0. We didn't change anything. It wasn't among these values that were changing. It remains 0. x2 would go to 2 from 0. S1 would be here. 2 here. 2 minus 2, 0. S3 would be 5 minus 2, it would be 3. S4 would be 3 minus 2, it would be 1. Am I missing something? Yeah, this is 2. This is 3. S4 would be 8 minus 2 equals to 6. And S5 would be 6 plus 2, which would be 8. Okay? So this would be my new point. So I started from this point. Now I went to this point. 0, 2, 0, 3, 1, 6, 8. Okay, so this was my first point. Now I'm in the second point. Yes?
Can you just repeat that?
This part?
Yeah.
Yeah. Oh, I got it from this way. So what's the new value for S? Let's call it S prime. S prime is the beginning value plus the amount of change in it. Okay? The beginning value for S1 was 2. The amount of change in it is minus the amount of change in X2. Amount of change in X2 is 2, minus it is minus 2. 2 minus 2 equals to 0. Basically, it comes from the same idea here. Now, let's see what's this point. Is it clear or no? I see some puzzled faces. Okay, I guess it's clear, but, you know, if you have still questions, ask me. You know. I cannot read your minds. Now, everything else aside, you know, this 7-dimensional thing, forget everything. Just look at these two. What happened? We were at 0, 0, we went to 0, 2. We were at 0, 0, we went to 0, 2. I even didn't know what's the equation of this point, but now I know. Now let's double check just to make sure we are fine. What's this point? This point is intersection of the first equation, the first constraint, with the line x1 equals to 0. The first constraint is this. Basically minus 2x1 plus x2 equals to 0. And x1 equals to 0. If you intersect them, x2 would turn out to be... I made a mistake here. Oh, this is 2. x2 equals to 2. So, that's a sanity check. Everything is nice. So we moved from here to here. Done. Now, the next step is to move one step ahead. This one is going to be much faster. I hope you feel comfortable with it. Now, again we are standing here, and now we have two directions again. First thing was to which direction to go. We can either come back our direction, or we can go this direction. We have to calculate what? The amount of change to see which direction is good. Even without calculating, we will know that this direction wouldn't turn out to be a good direction, because we know that in this direction we increased, when we go back we would decrease. So we would check this direction. If it's positive, if it's good, we would go in that direction. Otherwise we are fine. Feasible and also optimal. Good. Done. So let's erase everything because you won't need anything from these calculations. Okay. I don't need these. Okay. Now with this one we are going to do it fast. So we are standing at point 0203168 in our 7-dimensional space. First we have to check the directions that we want to move. So let's call this direction A, this direction B. If we go in direction A, So if you remember, when we were talking in matrix format, we called this P transpose X. Our P matrix was 1, 6. Our X matrix is X1, X2. So derivative of P transpose X is derivative of our objective function. In direction A, it would be just d of x1, d of x2, because only x2 changes. But in the direction, let's call this direction A. In direction B, we have a little problem. Let's see how we calculate it. It would be this guy. Okay, but we are going to change both of them at the same time. We don't know how to evaluate this for the time being. Let's see how we do it. We know that we are going to remain on this constraint. This constraint will not be violated. Okay, so wherever we go, constraint number 1, minus x2x1 plus x2 would equal to 2. So minus 2x1 plus x2 would equal to 2. And when we go to the new point, which we call it x prime, to the still remain equal to 2, because we are still on the same line. We didn't move anywhere. We didn't leave the line. We were here, we are coming here. So deduct them from each other, minus 2 delta, or let's call it dx1 plus dx2 would equal to 0. So we have a relation between x1 and x2. Between the change in x1 and x2. Plug it back here. So you would have, this would turn out to be, so this would have dx1 would equal to, dx2 would equal to 2 dx1. So if we put it back here, we will have 13 dx1. So 1 or 2, 1. Okay, good. Now, let's see. If we move in direction A, what will happen? Moving in direction A, you will decrease x2. So dx2 would be negative, your function would decrease. This is not a good direction. Moving in this direction, we are increasing x1. So dx1 would be positive, so our function would increase. So we start moving in that direction. Now there is one thing here that I want you to look at it. If you remember when we were standing at 0, 0, and we started writing these two, one of them turned out to be dx1. Let's call this direction 1 and direction 2. So in direction 1. And in direction 2, this thing turned out to be 6 dx2. So what, if you look 1 and 6, it's the same number as 1 and 6 here. This was just a coincidence. It's not always happening like that. If you look at it this one, in this case this is 1, well basically this is 1 and this is 13, which has nothing to do with the numbers here. These numbers that show up here, which tell you how much your objective function changed if you change your variable, they're called reduced cost. They have a name too. Okay. So if you just heard it, just to have heard of it, reduced cost means that if you change one of your variables a little, how much your objective function would change. That's also a name to remember.
13 came from the 13?
The 13 came from, we know that we are staying on the same line, nothing on line. So we know that the dx2 equals 2 dx1. Okay. So d of x1 plus 6 d of x2 is dx1 plus 6 d of x2. I replace it back there.
Excuse me.
Yes.
So just assume we were on dimension n and we will not have this graph. We will know that the constraint to consider is the first one because we hit the...
Okay, that's a good question. Whenever you assume that you're a three-dimensional one, three-dimensional would be good enough. And you're standing on a peak of a pyramid that has 4 directions. So what you will always know, where you are standing. And you know on which constraint you are. You have 4 directions to check. So each direction you pick it, then you know this is the equation, you find this guy and go ahead. You always know where you are and you always know where you want to go. But before calculating, you don't know where you will stop. The step might be very small, the step might be very big. You don't know that yet. Yes?
Like in this one, you were able to tell that x1 is increasing along this, so we go in this direction.
Exactly.
By referring to the graph.
It's not really referring to the graph because, well, because what we are thinking here, let me tell you what I said. Okay, for the time being, assume we are using graph. Yes. For the time being, assume that I'm using the graph. I don't want to go into details. You're right. But there is, in fact, this guy would turn out to be, okay, maybe I should write it. No, forget it. For the time being, assume we're using the graph. Yeah, yes.
What's the difference between shadow prices and reduced cost? Will you go over that?
Oh yeah, shadow price was something else totally. Well, these are just names. Don't worry about them. You will get notes on them exactly. I just want you to have heard of them so that you're not shocked next time in class. That's all. Now I'm here. I'm going to move here and see what's going to happen. Again, the same calculation and I'm fine. What's this calculation? The calculation would be to see how far I can go. So remember, we had two steps. Would you just listen to this one? This is very important. Just a second. So whenever you're standing at one point, you have to do two things. First, you have to look at directions and see which direction you want to go. So you stand here, you have two directions. You have to look at directions, see which one is better. Well, which one is good? Forget better or worse. Some of them are good, some of them are bad. That's all. You cannot compare them. You look at this direction is good. You start going in that direction. The next calculation is to see how far you can go before you hit a boundary. So again, we have to calculate so now we chose the direction that we want to go. We don't want to go to this direction. We want to go to that direction. Now we have to just check the boundary and see how far we can go. Now let's do it again. And then we are all set. Now, what's my basic vector here? My basic vector is x2, s2, s3, s4, s5. What's it? Basically the non-zero variables. 2, 3, 1, 6, 8. Okay? Now, I'm going to remain on these constraints, plus s1, plus s2, plus s3, plus s4, plus s5, equal. Still, I'm not going to violate my constraint. So the equality constraint with ss should always hold. Okay, so I have to write down my equations in a way that those hold. So, what's the first equation? The first equation is minus 2x1 plus x2 plus s1 equals to 2. Okay? Which value is going to change? x1 is going to change. Okay, s1 is 0. Okay, I don't care about it, and it's not going to change. Why it's not going to change? Because I'm standing on the same line that s1 is 0. I'm on the same line. I'm not going to leave this line. So s1 would remain 0. Nothing would go wrong with it. So basically it's as if this guy is not here. So, but from this line I'm going to go to a new line, which I call it this. So the change is 0 minus 2 dx1 plus dx2 is equal to 0. So this would tell me how my x2 is going to change when my x1 is changing. Now we have a nicer way to write it, the matrix way, that we just learned it right now. So it would be plus. Okay, let me just look at my calculations. I think I have a mistake here. Okay, I have to write it down first for you. That's fine. So look at these constraints that we have here. Look at the column that x2 is there. So that column is, the column that x1, because we are changing x1. That column is minus 2, 1, 0, 2, 2. dx1. So x1 is going to change like this. For the first constraint, we have minus 2 dx1. For the second one, we have 1 dx1. For the third one, it doesn't care where you go. Wherever you go, it doesn't matter really. Why? Because the second one is saying, the third one is saying x2 is less than or equal to 3. So if you change x1 wherever you go, who cares? Now, this guy plus. Now, all these constraints which were equality, the ones with s should hold still. So minus 2 dx1 plus dx2 would be 0. So this is x2 S2, S3, S4, S5. So X2 has a 1 here, and the rest have 0. This should equal to 0, 0, 0, 0, 0. So let's see what I wrote. I wrote minus 2 dx1. Sorry, I missed something here. dx2, ds2, ds3, ds4, and ds5 equals 0, 0, 0, 0, 0. So let's see what I wrote. I wrote down minus 2 dx1 plus dx2, the rest are 0, equals to 0. What does that mean? That means that this constraint would remain feasible. This constraint will not be violated. Then for the second line, I have 1 dx, let's write down the equation for the second one. x1 plus x2 plus s2 equals to 5. And we are going to remain on this line. Okay? So dx1 plus dx2 plus ds2 would be equal to 0. The amount has changed. So dx1 plus dx2, 1 plus ds2, but the rest don't show up, would equal to 0. Okay? Then for the third one, you would write it down. The third one, there is no x, there is x1. So basically, you should look at the pattern. You should just write down the column of x2s. So the column of x2 is 1, 1, 1, 1, minus 1. 1, 1, 1, 1, minus 1. So I just wrote down the column corresponding to x2 from there, here. I didn't do anything fancy. Now you have to write the column of S1, column of S2, column of S3, column of S4, and column of S5. If you remember when I was writing the equations in the beginning, I wrote them like this. S1, S2, S3. It was to emphasize that S1 is only on the first row, and the other rows are 0. This guy looks like this. So when you write down that matrix, it would be this. Sorry. Okay. Now, what I wrote down is nothing more than those. The last time I wrote the equations, this time I wrote the matrix. What did I say? They say that none of these equality constraints, plus S2 plus, would be violated. Now, solving this system of equations for dx1, assume dx1 is known, you solve for these 5 unknown variables, they would give you that how your variable x2 or s2 or s3 will change if your x1 changes. Okay? This is the most important point, and then the rest is just easy. So what I wrote down here, I just wrote down in matrix format instead of equation format how changing x1, if we change x1, how we should change the others so that we remain feasible. That's all I'm saying. Now, solving this would give you, for solving it is easier to write it in equations. Minus 2 dx1 plus dx2 equals to 0, so dx2 would equal to dx1. Sorry, 2 dx1. This one would give you dx1 plus dx2 plus ds2 equals to 0. So ds2 would equal to minus dx1 minus dx2. But from here, you know that dx2 is equal to 2 dx1. So this would equal to minus dx1, if I'm not mistaken. Oh, there's a minus here, sorry. So this would be minus 3 dx1. So the first line told me that if I change x1, I have to change x2 2 times that to remain feasible. And also, I have to change s2 minus 3 times that to remain feasible. Then I would find how I should change s3, how I would change s4, and how I should change s5. So how do I do that? I multiply this by this, bring this vector here, I write the same vector here, then I have a matrix here, I write down the inverse of that matrix, multiply by that, multiply this vector on the other side by that too, and then we are fine. Basically what I told was this. A plus, not A, let's call it B plus AX was equal to D, vector matrix is vector. So then I said we know that ax would equal to d minus b, then x would equal to a minus 1 d minus b. So this is exactly the same thing. You have these vectors, matrices. So you solve it, and you find x's. You find how the changes should be written. And I have done it, and you will find out that the changes should be written this way. Since I don't want to do the calculations here on the board. So dx2 would equal to 2dx1. ds2 would equal to minus 3dx1. ds3 would equal to minus 2dx1. You have to double check this. I might have made a mistake. 4dx1. And ds5 would turn out to be 0. Okay? Now, that's a good thing. What does ds5 would remain equal to 0 means? It means that in the fifth equation, if you change x1 and x2 accordingly, you really don't need to worry about s5. Don't change it. Just keep it the same. So this is just basically telling you how you should change your basic variables when one of your non-basic variables, x1, is changing. x1 was 0. We are increasing it. We had some other non-zero variables. We are worrying that these variables are decreasing. So we are worrying that these variables should change in a way that you remain feasible. This is the way that you remain feasible. Good? Now the last step is to see how far you can go. These changes, some of them would increase these variables, some of them would decrease. You should just make sure that those that are decreasing don't go below 0. You find the least one, you move there. Done. Let's see. The first one is x2. x2 was minus 2. So minus 2, let me write it somewhere that everybody can see. This is the last step on this method. So we have minus 2, which is x2. Minus 2 plus 2dx1 should greater than or equal to 0. So dx1 should be, sorry, I made a mistake. dx, that's right, okay. Now, the second one says s2, which was 1, plus the amount of change in s2, which is ds2, which is minus 3dx1. Minus 3dx1 should remain greater than or equal to 0. So dx1 should be greater than or equal to, should be less than or equal to 1/3. Oh, sorry. This is 3.
No, you're using the wrong variables, I think.
Yes. Sorry. I used the wrong variables. Sorry, my mistake. I have to use these variables. Sorry, my mistake. Totally my mistake. So, x1, x2 its value was 2. Now it's changing by the value of 2 times dx1 should be greater than or equal to 0. So this should be greater than or equal to minus 1. Sorry. Minus 1? That's right. Yeah, minus 1. That's right. Which is fine. Basically nothing goes wrong. Now, the second one, the value was 3. Now, I'm changing it by minus 3 times dx1. So minus 3 times, this is s2. Should be greater than or equal to 0, so this should be less than or equal to 1. The second one is s3. Its value was 1. ds3 is minus 2 times dx1. This should be greater than or equal to 0. So dx1 should be less than or equal to half. S4, its value was 6. ds4 is minus 4x1. This should be greater than or equal to 0. So dx1 should be less than or equal to 3 over 2. And the last one is S5. Its value was 8. It's changing by 0. Should be greater than or equal to 0, which is. So we are all set. So now we look at these bounds. This is the tightest one. So you have to increase x1 by half. You increase x1 by half and write down the whole thing. So you write increase x1 by half, you will have what? x1 from 0 goes to half. x2, change 2 times that. So 2 times the x1, 2 times half would be 3. So it would be 1 plus 2 would be 3. S1 doesn't change. It was 0. It remains 0. S2, it was 3. It changed minus 3 times of x1. Minus 3 times minus 3 half. So 3 minus 3 over 2 would be 3 over 2. This is 3 minus 3 multiplied by half. S4, which is this, S3, which is this one, we know it's going to be tight. It would turn out to be 0. Why? Because it started from 1 and it changes minus 2 times the x1. The x1 was half, so 1 minus 2 times half is 1 minus 1, 0. So this is 2 minus 2 times half. And the rest the same way. 6 minus, that's 4 times that, so 4 times 2, this would be 4. And 8 would be 8. So I moved from 0, 2, 0, 3, 1, 6, 8 to half, 3, 0, 3 and a half, 0, 4, 8. There are again 2 zeros, 5 non-zeros. Normally this happens. Now, we are in point half and 3. This is the point half and 3. So we started from here, moved here, moved here. Now you check your direction for yourself as a practice for the next one. You would see that this direction is still good. You go one more step, and then when you get here, both this direction and this direction would turn out to be directions that if you go, your function would decrease. So you would have reached optimal. Done. Alternatively, when you were here, you could have chosen this direction. Then you would have come here, 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 and then stopped. So one of them was just a shorter path. Well, I knew which one is easier, so I went that way. But no, in general, you don't know, and there's no way to know normally. There are ways to guess, but none of them are exact. This would turn out to be the optimal point. I'm not going to do the calculations for you. You do it yourself. Yes.
Which we know how to do this a different way, because I mean, again, a couple of us have done like the Tableau method.
Okay. Yeah.
Do you think he's going to ask us?
This is the Tableau method.
Well, this method will be written in a nice way that well, some of you might not have heard it. This is called the Tableau method. There's a nice table, and these calculations wouldn't be messy. Everything would be nice. It's easy to remember. But then in that one, if you don't, in fact, in that one, you can do it even without knowing what you're doing, and it's fine. You will get the solution, and you even don't know what's happening there. You just can add and it's good. There's nothing wrong with it. It's really good to know it, because then you would never make the mistake in the exam. This way, I'm sure you can make a mistake. But this one, this one has a good property, which you know what's happening. So yeah, I think he would. Either Professor Engel would teach you, or he might not even teach you, because it's not really important for us. We just want to know what's happening. That's all. So from this whole calculations, what I want you to remember is not how I did it. I want you to remember this, that I stood here, I looked at all the directions that I could go. It means I looked at the constraints that were active, I was standing on them. I'm now using these names that you might hear a lot. So some constraints were active, it means you were standing there. You looked at those. You looked at those directions and see which directions are good to go, which directions are bad to go. You picked one of those that is good. Anyone, doesn't matter for us. Then you started moving in that direction until you hit one of the other boundaries. When you hit it, you calculated it there, again the same story. And you continue. So this is called simplex method. There are other methods which are called interior points methods, which are these. For example, you start here and you say that the objective is here, so instead of going this way, we go this way. We go from inside. That's why we call them interior point methods. There are other methods. There are a billion methods. Yes?
You know how we looked at S3 and said the tightest one was dx1 is less
Yeah.
than half? Is there ever like a thing where you have dx1 is like less than half and you move that much but you don't get to the new point?
No, you will.
So it should always fit, right?
Yeah, you will always fit. Yeah, that's the whole thing. You will fit. It's because we are not doing anything magic here. It's just that we go. So the idea of less than half, it means that you go until you hit something.
Okay.
So until this guy becomes tight. If you go only 1/3, it means that you have moved and you stopped here. You had more to go. That's all. Okay. This is the idea of simplex. Then, okay, I'm going to skip some stuff. I'm going to talk about something called duality and also a little bit about MLE. So the duality part, you haven't covered it that much in class yet. We just talked about a dual variable and it has some interpretations. So that's what I'm going to talk about. We will talk a lot about next session in Professor Angar's class. Now, after we do all these things, okay, forget the whole story. Okay, now the whole story is changing. We are not concerned about solving the problem anymore. Now, we have solved the problem by some solver, whatever, Excel, who cares, and we have the solutions for this guy. Now, in real life, this is what's going to be useful for us. So these constraints are constraints, for example, on your working hours, your material, your things like that. Now, the idea is these numbers are all, well, forget that, estimate. These numbers are constraints, like you had 5 workers. You couldn't use more than 5 hours of his job. Assume it was well, let's 8 is better. You had 1 worker, he worked 8 hours a day, you couldn't increase it. Now this guy is willing to work overtime, 1 more hour. So you can change this 8 to 9. Okay? Now you want to see how much is this worth. How much your objective value, which would be your profit, whatever, is increasing. But there are 2 ways to do it. One way, solve the problem again. You can just write down the whole thing, solve it again, find the new objective value, and deduct the previous one from this one, and you would see how much it was worth it. That's one way to do it. But in our problem, it's possible because it is a small problem. But if you have a problem which takes, I don't know, 1 week to run, and you need the solution every day, then you cannot do it. So there are constraints that. So now we should think of some more clever ways to find these ideas. Each problem, LP problem like this, if it's a maximization, there is a minimization problem like that. Where there's a minimization problem associated with it. If it's a minimization problem, there's a maximization problem associated with it, which its name is dual. It has some properties. These 2 problems are totally different problems. They live in different spaces. They have no direct relation, you can say, to each other. But a lot of data of this one is useful on the other one, and a lot of data of the other one is useful on this one. We will learn how we will find this dual problem later on. So we are not concerned with that. What we are concerned with is that from solving that other problem, or even from solving this one, for each of these constraints, we will get a value called the dual value. So assume that each of these has, let's say, 10, 2, minus, well, no minus. 3, 5, 0, for example. So each of these would have a number associated with it, which we call it the dual value. The meaning of dual value is, if you increase this right-hand side by 1 unit, how much your objective would change. Okay? Now, obviously, if this is a greater than equal constraint, this dual would mean if you decrease it by 1, how much your objective would change. Basically, this would mean if you relax your problem a little bit more. So if you have a greater than equal constraint, relaxing it means lowering the lower bound. If you have a less than equal, relaxing it in inequality, it's a different story. Now, so this thing which is called the economic interpretation of the dual variables, because dual variables are nothing but the solutions to this other problem, which you would learn how to write it and solve it. So the solutions of me would just tell you how changing these right-hand sides would help you. These dual variables will give you other information too, which you would see in the Excel problem, that if you change these values, the parameters here, the prices, whatever, how much sensitive your problem is to that. For example, you want to reprice your products. I don't know. So these vectors would change. Then you want to see how your objective value or your solution would change. Then dual variables would give you that information too. On a harder level, if you change the vector, the numbers here. So what were these? These were, for example, product X1 wants 2 hours of work and product X2 wants 1 hour of work. Now you introduce a new technology, and instead of 1 hour, it would need 0.7. You want to see how this affects. There is also a method to see without solving the problem. All these ideas are just, without solving the problem, how this would affect that guy. This is called sensitivity analysis. Some of them are easy to do, some of them are hard to do, but we are really not worried about them, because if you look at the Excel output, it is giving you all these problems. You can just, we will learn one by one how to calculate them. Now, just to give a small graphic representation, what do we mean by increasing this guy, for example, by 1? Our optimal solution was here. So we were trying to push a line like, I don't know, let's say like this, as high as possible. Now, if we increase this guy a little bit more, this line, this point, is going to shift to this point, so our line can be shifted a little bit higher. Is the picture clear, or is it too much? Okay. I totally understand that this is not a good picture right now. Okay. So, assume I was maximizing this line, and this was my constraint. And these were the vertices. Now, if I shift this line a little bit up, like this, and these were my constraints. Instead of these 2 points, I will have these 2 points. So I can shift my red lines a little bit more. This is graphic representation of what I told you about this thing. Now, if I shift, okay, let me find a good one that would give me that idea. Okay, so these 2 lines always intersect here. Okay, now if I shift this line too much, it would go above the intersection of these 2 lines. So my feasible region would be this part, and being below this wouldn't contribute anything. So after a range, shifting it up wouldn't have any effect anymore. So these dual variables, all of them are valid in a range. More than that or below that, the geometry would be in a way that that effect wouldn't have. So basically, it's in a small area around it, small relatively. So with each of these dual variables comes a range. It tells you can change this variable in a range, and then your objective value will change with this rate in that range. After that, you normally have to resolve your problem. You can always resolve your problem, find the new dual variables, go ahead. So this is also the interpretation of the dual variables.
How do you gauge how big that range is?
How do you find the range?
How do you just gauge?
What do you mean? You have to find it? It's given to you, don't worry. You can find it with, well, all these things that I told you, all these numbers, have calculations exactly like this to find. We are not going to go through them anymore. Questions? Okay. Well, this is what I want you to remember from this picture, not these calculations, is what I want you to remember. Because this is the idea. The problem would always be solved for you by some solver. You will never see what's happening down there in the mechanics. But it's good to know that what's happening. You're just standing somewhere looking at directions, going in that direction. That's it. Now, there's one thing. How many of you know what MLE is? Maximum likelihood estimator. Question number 1 of the homework. Okay, some of you might not know. So let's just see what it is. And well, you don't need to. Okay. This is going to be 2 minutes. It's not that hard. Okay. Assume that you were conducting an experiment which, hello? So many people knew it and didn't tell me? So assume that you're conducting an experiment, and the experiment has 3 outcomes. 1, 2, 3. Well, let's say, okay. Assume you are rolling a die which has only 3 sides. Is it possible? No. You need 4 at least. Okay. Anyway, you have a random number generator which generates number 1, 2, 3 only, randomly. This is an experiment that you can do. And you know that the probability This is a little bit not my realm, it's Professor Witt's and Ruba's realm, but that's, let me just talk about it fast because we need it for that. So, now, each of these happened with some probability. Okay. We know that, by magic, that these probabilities are distributed this way. 1 would have probability of alpha, probability of 2 is 2 alpha, probability of 3 is 1 minus 3 alpha. I just know it by luck, I guessed it. I have some intuition that this works this way. Okay? Now, so I do go and start doing the experiment. I just do the experiment the first time. The first time the experiment gives me 1. The second one it again gives me 2. 1, 3, 1, 2, 1, 1. So I did my experiment just randomly, I told it give me random numbers. It gave me this number. Now, having these numbers, I want to estimate what alpha is. There are, at least I can think of 3 methods to find it. The most straightforward and most intuitive one is called maximum likelihood estimator. It's not necessarily the best one, but it's really easy to look at and it's intuitive. So let's assume that these were all independent trials. So we want to write down the probability of this thing showing up as a, this is just an event. So probability of x1 equals 1, x2 equals 2, x3 equals 1 until this. So since these are all independent, the probability of this and this would be just the multiple of the probabilities. Okay. So what's the probability of x1 equals to 1? It's alpha. Alpha. 2 is 2 alpha. 1 is again alpha. 3 is 1 minus 3 alpha. 1 is alpha. 2 is 2 alpha. 1 is alpha. 1 is alpha. So this is the probability of this event happening. Okay, nothing really fancy, which will turn out to be alpha to the power of 5, 2 alpha to the power of 2, 1 minus 3 alpha. Simplifying it a little bit, it would be 4 alpha 7 minus 12 alpha 8. Okay? So this is the probability of this event happening as a function of alpha. Now I want to find the alpha which maximizes this probability. So to differentiate it and set it equal to 0. So the differentiate, it will be 28 alpha 6 minus 96 alpha 7 equals to 0. Well, there are 6 zeros which are the solution, so we forget them. So 28 alpha minus 96 alpha equals to 0. 28 minus 96. So alpha equals to 28 over 96. Okay? So 28 over 96 is an estimate for alpha. Why we say it's a good estimate? Because it's the alpha which maximizes the probability of this event happening. It's just one way of estimating it. People have, so these are called MLE functions. Now, so when they say MLE, maximum likelihood ratio function, either they call this function, which is product of all those probabilities, or sometimes they call the logarithm of this. So sometimes instead of this, they take the logarithm of this function and maximize it. Since logarithm is a one-to-one function, it doesn't matter. It's the same result. It's just that working with logarithm sometimes is easier. Doesn't really matter. So either this function or its logarithm is called the maximum likelihood estimator. People have, discussed their properties, if they are good, they are bad, sometimes good, sometimes bad. Now, in real life, well, this was a very weird example. In real life, you guess that this phenomena, for some reason, you have some belief that it has a normal distribution. So you have a mu and sigma to estimate. You take samples, you do the same thing, but instead of maximizing the probability, you maximize the density. Density of that thing happening instead of the probability of that thing to happen. So you maximize, so you just write it down, differentiate. Yes?
For that case, would you have to take partial alpha?
You have to take partial derivatives because there are two variables, mu and sigma. So you take two partial derivatives, set them equal to 0, solve them at the same time. In this case, you have an exponential thing. So you have some reason to believe that this experiment is following an exponential distribution. But you know that the exponential distribution looks like this. There is only one estimator, alpha. So you write down the data, you plug it there, you find the density maximizer. That's called, yes?
What you mean is that you maximize on which direction? If you have several variables?
Yeah, if you have two variables, you have a function which looks like this.
But that doesn't give you the local maximum.
Oh, well, we are assuming that your functions are nice, everything behaves nicely. It will give you a local maximizer. Okay. So, in a two-dimensional thing like a normal, your function is, a sigma. For every case of mu and sigma, you will have a joint density. So you're trying to find the best combination of mu and sigma that would maximize that joint density. Derivative, set it equal to 0. Normally, all the distributions that we work with are nice distributions. They behave nicely. Nothing would go wrong with them. Yeah. So that's one way. There's a Bayes method, and there's also another method called translating, but I don't know the English name for that. I forgot. Method of moments, something like that. So all these methods, they try to come up with examples. They try to come up, with methods to estimate the best parameter. That's all. We really don't need to know. I just thought that you might like to know it because it shows up in the homework. So, any questions about homework?
For question 3A,
3A.
it talks about you showed this using second order and
Okay.
it's a maximum. Can you try to? I'm not trying.
Just take the second derivative and show.
But it's with x and y. Like it's got two variables. X
So
and
it's a
y.
Hessian, and you have to talk about if it's positive definite or not positive.
I forget how to.
So do you remember the Hessian matrix?
Uh,
Okay, the Hessian matrix was, correct me if I'm wrong, it was this, for a two-variable thing.
for
Two-dimensional thing.
and do you take the determinant of that?
Sorry? So basically, it's the matrix of the second order part. So if this matrix turns out to be positive semi-definite, or it turns out to be not
Take the determinant to get square root of the
not the determinant, eigenvalues. Okay, maybe let's talk about it later. There are different methods to find out if a matrix is semi-positive definite or not. It's not the determinant, it's the eigenvalues. And forget what's eigenvalue, there is this command in MATLAB that tells you if it's the eigenvalue. Or if you really, really want to know, there is a way. Okay, forget it. If you just didn't understand what I said, forget it. But for those that are interested, if you have a matrix which looks like this, just 4 numbers. For it to be positive definite, the determinant should be positive. Then the determinant of this part should be positive. Then the determinant of this part should be positive. Then the determinant of this part should be positive.
So just use MATLAB.
Yeah, you just use MATLAB. You don't do these things. These things you don't do them, never. You just say yes.
For number 4,
Number 4.
you have to do some sort of regression in order to determine volatility. What do you use an absolute value of this residuals or sum of square roots?
Sum of a square root. Always do. So when you want to minimize some error, always minimize the sum of the squared errors. You can always do it with absolute values too, but it's not linear. We want to do, well, not linear. It's not well behaving, Absolute is, doesn't have derivative at some point. We don't like it. So we like something which is, you can take derivative, nice, That's it? Okay. Have a good day. Okay.